In this chapter of kinetics, we'll be studying about the rates of reactions, the factors which affects the rate of reaction, how fast or how slow the reaction takes place, different experimental techniques to measure the rate of reaction, and also the collision theory. And that first part of the lesson, which I'm going to complete today, is nothing new but what you have done for your levels. And the second part involves the Maxwell-Boltzmann distribution curve, right? That is the A-level part, right? Of course, this is also in the A-level syllabus, but you have done this for your levels. So I'm going to just quickly go through the first 9 or 10 pages up to about, I think, page 10. Just going to rapidly go through those because already we have discussed the basics for the O-levels. So the rate of reaction simply explains how fast or how slow a chemical reaction takes place. So in a chemical reaction, as you know, any chemical reaction is a bond breaking and a bond making process. Any chemical reaction is a bond breaking and a bond making process. So what happens here is that at the reactants, the bond breaks, the atoms rearrange and form new bonds, and new products are produced. So during this process, you will see a chemical change taking place, meaning some reactions give out a gas, some reactions produce a precipitate, some reactions, the reactants are solids, but as a reaction progresses, solid will disappear, solid will react. So there are different observations observed based on the different type of reaction. And also, you will see the reactants in any reaction disappear. In some reactions, these reactants disappear and the products appear. So we can measure the rate of reaction in terms of the rate of disappearance of the reactants or the rate of appearance of the products. So this way we can measure the rate of reaction, right? So it can be even a concentration. You know, the concentration of the reactants decreases with time. As for the product concentration, that will increase with time. So it can be the measured factor can be concentration, it can be volume of gas, it can be mass of reactants produced and mass of reactants used. So any measured property. So in a rate of reaction, we study how these measured properties changes with time, right? And unit time, given unit time, how these changes occur is what we study in kinetics. So if you express the rate in terms of concentration, then we know the concentration unit is moles per decimeter cube, and the time is measured in seconds. Then the unit for rate will be mole per decimeter cube per second if the rate is measured in terms of concentration. So these reactions can be classified into 3 main categories: a slow reaction, moderate reaction, and fast reaction. Fast reactions, we know potassium, sodium reacting with cold water is an example for a fast reaction. An extremely slow reaction is for example, rusting of iron. It takes days and months, days and weeks, right? Very extremely slow reaction, rusting of iron. As for a moderate reaction, reactions such as magnesium, which is a moderately reactive metal, reacting with acid is a good example for a moderate reaction. So let's try to show these 3 types of reaction in a graph, a rate graph. A rate graph, the independent variable, which is the variable being manipulated, comes to the x-axis, and the dependent variable, which is the observed effect of the independent variable being manipulated, comes onto the y-axis. That's like any other graph. So here we study how with time the amount of products vary. So the time becomes our independent variable. So for a fast reaction, you see the products produced at a very high rate and reaction will come to an end at a lesser time. This example for a fast reaction. The same fast reaction, if you do some changes in the conditions, you can convert the same fast reaction into an extremely slow one. It takes a long time for it to complete. This is a slow reaction, right? It's the same reaction because you can see the products are in the same levels at the end, Just because reaction is slow doesn't mean it produces less products. No, it produces the same amount of products at the end of the reaction, but it takes a long time to produce that amount of products. For a moderate reaction, it takes a moderate amount of time. So this is moderate. This is the T fast, time taken for the fast reaction to complete, T moderate, and T slow, time slow, right? 3 types of reactions. So you can make a slow reaction moderate, a moderate reaction fast by altering certain conditions. Let's see shortly what are these conditions and how those conditions can be altered to get the 3 different types of reactions. Please copy this. Let me know once you're done. So the rates of reactions can be measured in terms of reactants. That means reactants used up per unit time. Time can be in seconds if it's a fast reaction, or in minutes if it's a slow reaction. And of course, the amount of products also can be used to measure the rate of reaction. So there are different ways we can use. If a reaction produces a gas, you can record the volume of gas per unit time. And if a reaction produces, a solid precipitate, can analyze the time taken for the precipitate to appear. And if it takes the reactants, then decrease in mass. For example, solid get used up, then decrease in mass can be used to measure the rate of reaction. Different ways based on the experiment. So when you collect this data, you plot a graph of the x-axis, time being the x-axis and the measured factor being the y-axis. That's called the rate graph. And the gradient of the rate graph will give you the rate of reaction. For example, if I'm to draw a graph which is a concentration of the products versus time, get like this. So this is the point where we say the reaction should be exactly horizontal, parallel to the x-axis. This is the point where we say reaction has come to an end. That's in terms of the products. In terms of reactants, we know reactants get used up, right? So if I need to find the rate of this, what you can do is that rate differs each and every second, because each and every second we see different amount of products produced. So what you can do is to find the initial rate, you can draw a tangent here and find the gradient, which is the tan theta value, which is a gradient, which is y distance over x distance, right? That will give you the rate of reaction. You can see the maximum gradient at the initial stages. That's the initial rate. And if you need to find the rate at a given time t, you can say, for example, given time t, then you can draw a tangent at that given point. And then you can draw a tangent there and calculate the tan theta value, which is the gradient, the y distance over the x distance, right? This is tan theta, y over x. This is at time t, the rate at time t. So you can see the gradient is less, right? It decreases with time. The rate of the reaction decreases with time. Eventually, at this point where reaction is completed, the gradient will be 0, right? So initially the rate is maximum, and then it decreases, and eventually goes to 0. Likewise, with respect to the products, react with time. So you can draw the initial gradient, find the initial rate by this method, drawing a gradient, the tangent there, and finding the gradient, or you can find the gradient rate at the time t. This is again the y distance over x distance. That will give you the gradient. So gradient is tan theta, which is y over x, and this is the rate at time t. So this is the initial rate and the rate at time t, right? So horizontal graph means the reaction has come to an end. Let me copy this. This is the here the gradient equals initial rate. Here the gradient equals rate at time t. That's right. The second graph, the gradient is negative. Rate can be negative or positive. With respect to the reactance, rate is negative, right? Just cover this. So 1 upon time. Now see, generally we take 1 upon time as the measurement of rate. Look at this. The rate is directly proportional to 1 upon time, which means if a reaction is extremely slow, that means what? It takes a long time, right, to complete. If a reaction takes a long time to complete, that means it's a slow reaction. That means the rate is low, right? So if it takes a long time, it's a slow reaction. If it takes a lesser time to complete, that means a fast reaction. So rate is inversely proportional to time. In fact, 1 upon time is often used as a measurement for the rate. Right? That means if you're plotting a graph, say temperature versus rate, you want to study how temperature affects the rate. So temperature is your x-axis, that's the independent variable. That means you're studying how temperature, change in temperature affects the rate. So temperature becomes the independent variable, and the rate is a dependent variable. Now, how can you measure the rate now in this graph? So you take 1 upon time as the measurement of rate. In that case, the units of rate will be per second. Per second. Right? There are 4 factors which affects the rate of reaction. Temperature, as we are discussing O levels, concentration or pressure, particle size or surface area, and catalyst. Now, the concentration or the pressure is one factor. Concentration is used to explain how the rate is affected by the concentration of a solution. For solutions, we use the concentration, and for gases, we use the pressure, right? Pressure. So it's the same factor. And particle size, surface area is same factor. So we'll discuss about these factors in detail, how these factors affect the rate. Now, explanation, how these factors affect the rate is explained using collision theory, right? There are 3 points in the collision theory, right? So let me explain to you one by one. The first point of the collision theory emphasizes on the importance of the frequency of the collisions between the reacting particles. And what is meant by frequency of the collisions is the number of collisions per second. It's not just the number of collisions, it's number of collisions per second. So in short, we call it as the frequency of collisions, which means if the reacting molecules, if they collide frequently, that means number of collisions per second is more, the frequency is more. If the reacting molecules collide frequently, then that will result in increased rate of reactions. If rate of the reaction, because if reactants are meeting together often, then that will react to form the product. Right? So that's the first point, which is the frequency of collisions or the number of collisions per second. So increased frequency of collisions or increased number of collisions per second will increase the reaction rate. So how these 4 factors, temperature, concentration, surface area, and catalyst, how these 4 factors affects the rate is explained using this collision theory. Right? Now listen, it's important to mention the frequency of collisions, not just the number of collisions. If you say number of collisions, increase number of collisions, increase the rate of reaction, that is wrong. Rather, you should say increase number of collisions per second will increase the rate of reaction. So number of collisions per second, in short, we call it as the frequency of the collisions. That's the first factor. Clear? The second factor is the rate, is affected by the energy of the collisions. That's the second factor, the energy, important the energy of the collisions. We know the reacting molecules should have minimum amount of energy to collide and bombard and form the products. You need to break the bonds of the reactants, right? First, to start a reaction. To break the bonds of the reactants, you have to supply energy. This is the minimum energy which is required to start up a reaction. In short, we call this energy as the activation energy. Energy required to initiate a chemical reaction. So, no point increasing the frequency of the collisions, right? You also have to make sure those colliding molecules have energy equal or greater than the activation energy. If the colliding molecules have energy equal, or greater than the activation energy, then those molecules will collide and form the products. So in fact, more than the frequency of the collisions, the most important factor will be the energy of the collisions. No point increasing the frequency if the reacting molecules does not have sufficient energy. They're not going to collide and they're not going to react. Clear? So the greater number of molecules with the energy higher than the activation energy will result in greater frequency of collisions. I mean, greater collisions, number of collisions per second. That will